students. We are going to start a new chapter, and that is waves. Now we have come across oscillations, and we have seen that oscillations is a behavior that any kind of particle or any kind of matter exhibits. What is that behavior? The behavior is that they retrace the same path again and again. Okay, so in that oscillation, uh, we know the motion is periodic, means after some certain amount of time it repeats the same path again and again. So any kind of oscillation can be periodic motion, but there is a certain type of periodic motion which is called SHM, simple harmonic motion, which is the ideal case when every time, when the time duration it takes to complete a whole revolution is same for all of the oscillations, like all of the revolutions. Okay, so let's say the first revolution it has taken time 5 seconds, so in the next revolution also it will take time 5 seconds as well. And we know that there's something called equilibrium point, from where the body this is the place where the body wants to rest. Okay, so let's say this is the body at equilibrium point, and it is going this side, and again it is coming to this side, and again going like that, and this thing is happening again and again. So we know that in case of SHM there is something which is called restoring force. Now this restoring force always works towards equilibrium point, right? So we can say one thing here, that this kind of oscillation is SHM when first the restoring force is proportional to the displacement, and it is always directed towards the equilibrium point. That means it will be in the opposite direction of the displacement that is taken part by the particle. Now in case of waves is a kind of a propagation of disturbances that is going on. Okay, now what will happen, let's say we have lot of particle one after another. Sorry, we have lot of particles one after another. Now what will happen if one particle start oscillating? We know in matter all of these particles are somehow in some kind of attraction to each other, means they have some interaction between each other. It may be van der Waals force, or it can be hydrogen bond, or any kind of other bonds even. So when these things start oscillating, that means the first particle is having some certain amount of energy because it is oscillating. That means someone has already initiated an oscillation in that particle. Now what if say it's kind of that the first particle is holding hand with the next particle like this. So if it is holding hand with the next particle, when it is going up, it will also pull the next particle along with itself. So as a result, what will happen, this first particle will move up, so and the next particle will move little bit because it is pulling, and accordingly what will happen, we'll see the next picture like this. Now similarly, because the second particle is also holding the hand with the third particle, it is also pulling that particle upside, right? So as a result, what will happen, this third particle also move with itself. So if we just thought about the whole process, that means the energy of the first particle is somehow being transmitted to the next particles. Okay, so one after another. So what we will get finally, we will get something which looks like this. That means energy is flowing through each of these particles. Okay, that means a flow of energy is happening right here from the fast particle itself. So we can see that in case of this propagation of energy, each of these particles is also having some kind of oscillation. So cumulative or successive oscillations of all of these particles is actually responsible for the propagation of that energy. That means the wave is created by a collective oscillations of each of these particles. Okay, so we can see that this kind of thing is called a wave when disturbances or the oscillation or the energy from the fast particles is transmitted through the whole media, then it is called a wave. So we can say that wave is a collection of oscillations through which energy can transmit from throughout the media. Okay, so this is the wave. Now we have already talked about oscillation, and we have seen that the displacement in oscillation can be written as y is equal to a sine omega t. So what is omega? Omega is the we know that omega is nothing but your 2 pi by t, that is the angular velocity, and t is the time. So with this formula we can find out where this fast particle will be, okay, whenever the time is given to you. Now similarly we will proceed a same approach towards wave also. Okay, now let's start about the wave. So waves can be of different format. Like there is something which is called electromagnetic wave. So we can say EM wave, electromagnetic wave. We have something called mechanical wave, and we have something called matter wave. And what types of waves are there? Okay, so EM wave is nothing but your electromagnetic wave is a oscillation, mutual oscillation between your electric field and magnetic field. So what is happening right here? Here nothing but the energy itself is oscillating in such a way that the we know that the electricity and magnetism has a mutual understanding between themselves. How? Like whenever the electric field is changing, it creates magnetic field, and whenever magnetic field is changing, it creates electric field. And in this way these two fields oscillate and they create each other one after another, and as a result the whole thing, the whole energy propagate in a certain manner, and that is called EM wave. What is your mechanical wave? Mechanical wave is that kind of wave which occurs in matter, like in some kind of material or in some kind of media, when we have particles which are having interaction between each other, like the previous example which I have given you. As a result, what happens? This particles start oscillating and they transmit energy to their neighborhoods, okay, neighbor particles. As a result, the whole energy transmit in a certain way, and that is called a mechanical wave. What is a matter wave? A matter wave is a certain kind of wave which is linked to your quantum theory. Actually, it occurs mainly, it is noticeable for very small particles like electron, proton, ions. When this particle moves in very fast motion, these particles creates oscillation, okay, like create some kind of wave, but that is not actually your physical wave. We will come back to that. This is a little bit complicated. Okay, but we have this in our further studies, so we will come back to that. So this kind of examples are there for waves. Okay, so these are the examples. This is not a classification, but you can see, yeah, these are the examples of waves. Now waves can be classified in two ways. One is your progressive wave, which moves, progressive wave, and one is your stationary wave. So what is a progressive wave? A progressive wave is a certain kind of wave which propagate, because you can always look at the name progressive, that means it's propagate. That means it is not a wave which stands in a place. Okay, yeah, the energy is transmitted in both of these cases, but if you look at the wave you can understand that, yeah, you can realize that, yeah, the wave is the whole shape of the wave is propagating actually. But if you talk about stationary wave, this is some kind of wave which energy is, yeah, energy is somehow being transmitted, but apparently when you look from the outside it seems that the wave is not moving at all, it is standing in a fixed place. So this kind of wave you generally see in your musical instrument or string, okay, like a guitar or something like that. So in those cases you can see that if you just uh, give a little disturbance to the string, it generally creates some sort of wave like this. So this occurs most of the time when there are constant, like you can see here the spring is fixed and here the spring is fixed. So this kind of situation can create the stationary wave. Whereas progressive wave, it does not have any kind of, it does not have any kind of such just what you say boundaries or some constraint like that. It can propagate, so you can directly see that the whole envelope or the whole shape of the wave is actually propagating. So we have talked about already EM wave, mechanical wave and matter wave. Out of that, EM wave also exhibits sometime propagation, propagative wave kind of behavior. Okay, and your matter wave also you can see that thing. Okay, but generally we will talk about stationary wave with our matter wave itself. Make sorry, the mechanical wave itself. Yeah. So these two types of waves are there. Now in propagative wave we have again two type, and in stationary wave also we can see two type. Okay. So wave can be classified on basis of their motion, or you can say their propagation, like this way. But if you talk about the another kind of classification, depending on their way of moving, or you can say the way of oscillation. Okay, we have two types of, again, what is transverse wave and another one is called longitudinal wave. So this, see this, we have here we have two kind of classifications and here we have again two kind of classifications, but this classification is based on their motion and this classification is based on the oscillation they are actually having. So I say that when we have a particle, a string of particle like this, and when one particle start oscillating, the energy flows from first particle to other particle. So the way so the direction of the flow of energy is this side, whereas the oscillation is occurring in a vertical side. So you can see that the oscillation is perpendicular to the flow of energy. This kind of wave is called transverse wave. Whereas if you talk about a spring, if you talk about a spring, and let's say suddenly you have give an impulse to the spring, what will happen to the spring? The spring itself will transfer your energy to the end corner as well. But how? What will happen? The spring will create disturbances in terms of compression and decompression. So the oscillation will become in horizontal as well, whereas the energy flow is also happening in horizontal way. So how it will look like? We can again draw it and see that somewhere it will be very closed, whereas somewhere it will be longer, again closed, again longer, and that means here we have decompression, here we have compression, here we have again compression, here we have decompression. So in this way energy propagates. So this place where you can see the decompression is there. The next time, like after some time, this place will be again compression zone, and where you can see compression now. After some time, there we will see some decompression. So this is the way of oscillation in case of longitudinal wave. So if you talk about some example, so we can say that electromagnetic wave, or especially we can say light, which is a part of electromagnetic wave, is a transverse wave, whereas longitudinal wave is nothing but your sound. So we know that the sound is nothing but the vibration that we create in our vocal cord, and this vibration carries the energy through the media, that is your air in that case, and then somebody can catch it with their sense, right, with their sensor. So this kind of thing, that is sound, is nothing but your longitudinal wave, and light is your, or EM wave is your transverse wave. Okay. Now we will talk about some basic property of wave, and then we will come to the next part. Okay. So we have seen that there are two kind of wave. One is generally we will talk about these two classification, transverse and longitudinal. Okay. Later on we will come to this two. Acha. Or we can do one thing, we can talk about the progressive wave in terms of progressive wave, and then we will again move to the stationary wave. Okay, talking about very general properties of wave, I am drawing two pictures. So this, if I draw like this, that means the energy is flowing in horizontal, whereas the oscillation is happening in vertical direction. So this kind of wave is called a transverse wave, right? Okay, and if I draw something like this, let's say I'm drawing like this, let's say this is air media, and the air is compressed here and decompressed here, again compressed here, again decompressed here. So this kind of situation is nothing but your longitudinal wave, right? So if this is the starting point, let's say A is my starting point, so I'm just drawing the axis, and this is your displacement. So from here, so you can see that in this position, in this point A, the particle is at equilibrium point, whereas here the particle is at the extreme point. So this displacement is called your amplitude, the same as your oscillation. Okay, so this maximum displacement of each of these particles is called your amplitude. So A is your amplitude. In case of your longitudinal wave, you can see that the maximum separation, or so in case of longitudinal wave we have some different approach. but general study we will use transverse wave. Okay, so whenever we will study the longitudinal wave, what we will do, we will convert this longitudinal wave into a, a way of representation of transverse wave. So actually longitudinal wave cannot be converted into transverse wave, but for the sake of our simplification or analysis, what we will do, we will compare this longitudinal wave with some equivalent part of transverse wave. Okay, why? Because if you see at this thing, very difficult to tell where the actual point is, like where the point of compression is lying actually, because this is nothing, we cannot draw like that, right? We cannot represent this thing as a graph. So what we will do, we will convert this into some equivalent transverse wave, okay, which is having the same kind of behavior. So all of these waves we will analyze through this diagram. Okay, so this is the amplitude. This part where the particle is at extreme points, this parts are having some names. So the upper part is called crest, and the lower part, these two are called dome. Okay, so crest and dome. Okay, so from one crest to another crest, or you can say from this beginning A point to this beginning B point, or from C to D point, that is two crests, this distance is called lambda, that is a wavelength. Now we know that these particles are oscillating, right? So the first particle will pull the second particle, and the second particle will pull the third particle. So in this way the energy will propagate. Now if you look from the outside, you will see something like this, the pattern will be like this as well. So we can say that this distance is the distance where this first particle start. See, A is the point when the first particle is at rest position, and that means the starting of the wave. And again the energy is going through in certain manner, and at B position again the particle is at rest. That means if you talk about the first particle, by the time the first particle comes to rest after a full revolution, okay, and that in that time this particle at B will again complete a full oscillation as well. So this distance is called your wavelength. Okay, this distance is called your wavelength. Now this distance is your wavelength, so you can obviously you can always realize that this size is not your omega t, like that. Okay, yeah, this is omega t, you can always express like that, but this is not that oscillation part, you, or like something like that. Okay, you can see that lambda is a length, right, whereas omega t is actually nothing but your theta. So that is your angle, that was your angle, because omega is theta by t, right? So that means this is not something like omega t, because we are expressing here as length, the horizontal side axis is my length, some sort of length. Okay, so you can see that this distance is lambda, so AB is lambda, CD is again lambda, right? Acha, what is the time period? So from A point to B point, a full revolution, or you can say a complete wave energy is going on. Like let me make you a better simple statement. I said that the first particle which is at A complete a full oscillation, and by that time the particle B starts the oscillation. So that means the energy after the full oscillation of particle A, the energy is transmitted from A point to B point. So from A to B, this part is been done in some time, right? That time is called your time period. So in for the energy to come from A point to B point, that time period is called time period. Okay, that the time duration is called the time period. And what will be the frequency? The frequency will be again 1 by T. That means the number of this kind of wavelength, complete wavelength occurring per unit time. Okay, that means per unit second, how many wavelength is being completed, that is called your frequency in that case. Okay, so the frequency of this oscillation is different thing, and the frequency of that this wave is different thing. So when we treat oscillation, don't mix these two things. When we treat oscillation, we talk about the individual particle. We talk about the motion of these individual particles, right? But when we talk about this wave, we are talking about the collection of or the collective behavior of this whole particle. A lot of particles are there, and we are talking about the flow of energy through these particles. Okay, so there is the main difference. Oscillation, wave is being created by a lot of oscillations which are occurring successively. Okay, uh, and oscillation is only concerned about the single particle motion. Okay, so this is wavelength and this is your frequency. Now one more thing I will tell you here. You can see that the flow of energy or the length of the wave is dependent somehow with your wavelength. That means more the wavelength, more the length, right? So the displacement is somehow related to your lambda as well, and we will come to that later on. So the propagation, not displacement, I should not tell like that, but the propagation of the wave, that means how much it is going, that is somehow related to lambda, but we will come to that after some time. Okay, now because one more thing is there, because the wave is propagating in some certain direction, we have some vector which is called propagation vector. Propagation vector is k, which is your 2 pi by lambda. Now you will say, now the main problem is here 2 pi. How phase is again angle is coming. So I said you that because we are converting all of this wave into this diagram, that is in this kind of transverse wave diagram, even the longitudinal wave also we will treat using this diagram. Okay, we will convert that thing in some equivalent form of this oscillation, this wave, and then we will analyze. So we don't talk about displacement directly, that how much the energy has come from this place to that place, because one thing you see, energy is not a particle, it's a certain form of what you say entity that transfer from one body to another body, and we can only realize that by the interaction of that body, right? So we cannot see that when the energy is coming from A to B, right, like that. And so what we do, we usually again uh, take angles as some abstract thing, okay, as some abstract displacement you can say. So we say that this whole wavelength is completed when the total angle completed by this wave is 2 pi. So that means this place is your 2 pi angle. Okay, so let me write, so a complete revolution you can say again like that. Okay, actually that 2 pi we are taking in case of oscillation, right? But when we are studying wave, then also to understand the motion of the wave, we take help from the angles, and we say that when 2 pi angle is covered, in that means the whole wavelength has already been crossed. wavelength is completed, like that. Or you can say that the energy has come from some certain point to some certain point in that time period. Okay, so this point will be your 2 pi, this point will be your pi, this is your 3 pi by 2, this is your pi by 2, and this is your 0. Okay, so again we are taking help of these angles, and we can see that here this k is 2 pi by lambda. Now what is this 2 pi by lambda? So we can see that lambda length is being covered when 2 pi angle is crossed. Okay, so unit length is covered when 2 pi by lambda length is crossed. So this is your, sorry, angle is crossed. So this is a relationship between length and that abstract angle which we have taken for consideration. Because see, length you can measure from here, but angle we cannot measure like that. But for the sake of our analysis, we have taken angle to simplify our analysis. Okay, so what is this k? K is nothing but the angle covered in unit length. Okay, so that means it's kind of conversion between angle and length. So in unit length, how much angle is covered by this wave, that defines the propagation vector of that wave. Okay, so k equal to 2 pi by lambda. Acha. One more thing we will come here. Because this term will come in your further study, so I thought we should talk a little bit about it. Achha, one more thing is there, again omega we can express here even, that is your 2 pi by t as well, like oscillation. Here t is nothing but the time required for a complete lambda, okay, or a complete revolution you can say of this, when the 2 pi angle is crossed, you can also say like that. Acha. So that again gives us omega, but this is not the omega of oscillation, this is the omega for wave motion, okay, for the motion of the wave. So this is angular velocity of wave. Okay, fine. Now we have some general formula for wave as well. Now you have seen that here I have shown that the wave is started from here, like that. But what if I take the wave from here? I can take the wave from in the midway. So the starting is an issue. Okay, so it can start from anywhere, right? So the general formula for wave is something like this. General formula for wave. So we are talking about the propagative wave. So y is equal to, so y is nothing but again your displacement. Y is equal to a, which is your amplitude, sine, because it repeats itself, so it's a sine or cos function, kx minus omega t plus phi. Let me describe all the parts. So this is nothing but your amplitude. This is your propagation vector, that is 2 pi by lambda. This is your angular velocity. This is the time when you want to know the y, and this is your phase. Now this is something which is really important. What is a phase? So phase is nothing but your starting point, you can say. So this is the general formula for wave. So for very simple case, we take that the wave has started from theta is equal to 0 degree, right? But for many cases it happens that the theta started from pi by 4 radian or pi by 6 radian. It can start from anywhere, right? For let's say cos function, the theta will start from 90 degree, that is pi by 2, right? So we can see that in pi by 2 it will have some sort of displacement. So to measure that thing, so what I can do here, I can take this as my starting point, and I can just add this much of angle with that, and this is that angle. Okay, so this phi comes from the starting point itself. Okay, from where we are taking the origin. Based on that, this phi comes. Now we need some relationship between phi and the displacement. Okay, so we have seen that when 2 pi angle is covered, so after a lambda time, that means after a lambda distance, right? So lambda distance will cover 2 pi angle, right? So what unit distance will cover 2 pi by lambda angle, which is nothing but your k propagation vector. So x distance, any sort of x distance, will go 2 pi x by lambda angle, and this is called your phi. Because see here, whenever we have some sort of thing like that, where the starting is a little bit abstract, a little bit odd, that means we don't have some starting from zero, we can only understand this displacement, right? But this displacement is your y, not x. What is your x? Your x is this displacement, horizontal displacement. That means the displacement of the energy, or you can say how much the energy has been transferred. So if I know that, if I know the distance from here to here, if I know this distance, I can always find out how much angle is being crossed here. Means how much angle we have to add. Okay, so this is nothing but your phase. So that means this thing is nothing but your phase. So phase phi, that means angle covered in x distance, any sort of distance, that is your phi, that is 2 pi x by lambda. And this formula is very important for your upcoming days. So learn what is phi. Phi is nothing but your phi is nothing but your additional angle that has been introduced in your in your starting point. Okay, k is nothing but your propagation vector. So based on k, how much the wave is propagating, we can understand. Omega t, you know that with time, because see, only this term is there which will define the flow of energy. Why? Because with time the sign function will change. As a result, this y will even change. Okay, if we differentiate, so what is this y? This y is nothing but your displacement in vertical way. That means if this is the wave, then this will be the y, and this x which I have written here, that is nothing but your horizontal displacement. That means the how much the energy has been transferred. Okay, so these two things are different. Now if we differentiate y with respect to time, we will get the velocity. Okay, we will get the velocity of the wave itself. Now the next part, like the velocity and all those things, we will talk in our next class. For today, this much is the class. I think there should be many doubts regarding this class. So in the next live class, we will talk about it. You can ask me anything so that we can have a clear discussion about it, because it's an abstract part. You can say that wave we cannot generally realized like that, but these all things, like this whole formula, is something which is abstract, and which we have introduced just to analyze the properties of the wave. Okay, so bye bye everyone, we will see in the next class.